So imagine an engineering scenario. You've got a pipe, and the pipe's inner wall has been coated with sugar, and you let a fluid pass through the pipe. And what happens is that the sugar that was initially coated on the inner walls of the pipe starts dissolving into the fluid. And so this is a scenario what's called a convective mass transfer. So what's happening is that the flow of the water creates the convection because of which the mass of sugar that was on the wall of the pipe initially gets transferred into the fluid. So in a situation like this, for example, you want to understand how the different variables that are coming into play in this particular situation form a relationship. So, in any kind of experiment, what we normally like to do is we like to gather the variables and we like to fix all the variables except one, and we vary that one variable a couple of times and try to see how this one variable affects the entire experiment. Now, this way of finding a correlation in an experiment is pretty common and it's very effective at times too. But as soon as we start talking about uh, a lot of variables, for example, more than four or five, doing something like this by that method becomes extremely complicated because you have to conduct that experiment so many times, and the more variables there are, exponentially more you have to do the experiments. So it's not the most effective way of going about this. So there's another method though, and that's called the Buckingham Pi method. And what it does is it basically uses the various variables that exist, and without any experimentation, it can, in a way, shrink the number of variables that affect the experiment. So, for example, how it achieves this is that it creates these things known as dimensionless parameters, and these dimensionless parameters are basically parameters that are made by the combination of the original variables. And so what we try to do is try to find out the different dimensionless parameters that exist in the experiment, and we gather data in for those dimensionless parameters, and we try to find a relationship between these values. So in the case that I just talked about, what happens is we have six different variables, and we find out that there are only three dimensionless parameters that are coming into play in this experiment. So immediately it becomes so much easier to find a correlation between three dimensionless parameters versus six different variables. So let's take a look at the mathematics behind it and get to understand it a little bit better.
So let's start off by making a list of all the variables that we think will matter in a problem like this. So we have water flowing into a tube. So we already know that the density of the fluid is going to matter. And then we have the viscosity of the fluid, and then the diameter of the pipe itself that's going to play a role. And then we also have what exact velocity the fluid is coming in with. And then since sugar is dissolving into the fluid, there's a mass transfer happening there, and there's also a diffusion happening. So we can conclude that the diffusion coefficient is also going to play a role, as well as the mass transfer coefficient. So let's go ahead and make a list of that. All right. So the relevant variables. That's tube diameter, then fluid velocity, and then we have fluid density, and then fluid viscosity, and then mass diffusivity constant, and finally the mass transfer coefficient. So just to make things easier later on, I'm going to represent all of these variables by their symbols. So that's going to be a d for diameter, v for fluid velocity, rho for density, mu for viscosity, dAB for the mass diffusivity constant, and finally Kc for the mass transfer coefficient. So let's go ahead and write down all the units of these variables. And for the Buckingham pi method, we're also going to list all of their dimensions. So let's go ahead and do that. The units, first of all. So the unit of diameter is simply meters. We know that. The velocity is going to be meters per second. Density is going to be kilograms per meters cubed. Viscosity is going to be kilograms per meter per second. And then diffusivity, that's going to be meters squared per second. And finally, the mass transfer coefficient, that's going to be meters per second, same as velocity. So let's go ahead and write down the corresponding dimensions. Meters is simply length. Meters per second is length per unit time. Kilograms per meters cubed, that's going to be mass times mass per unit, length cubed. That's going kilograms per mass per second. That's mass per length per unit time. And then this one's going to be length squared per unit time. And then this one is finally going to be length per unit time. All right, so we have this table. Now what we're going to do is basically make another table, and this time they're going to include all of the dimensions that we have listed here and all of the variables. And we're going to assign each of the variables a unique score based on how many dimensions they have. So what I mean by that is basically, so let's write down variables first. And then we have our dimensions. So let's make a table out of this. Right, so let's take a look here. What are all the different dimensions that we've collected so far? We have length, we have time, and we have mass. I think, yeah, those are the only three variables that we get here. So let's write those down. So here's length, and then mass, and then time. All right, now let's make a list of all the variables that we have again. So we have diameter, we have fluid velocity, then density, diffusivity. My bad, that's not diffusivity, that is viscosity, then the diffusivity constant, and finally the mass transfer coefficient. All right, so what score we're going to assign each of these variables is going to depend on the dimensions that it has. So what I mean by that is, for example, let's take a look at diameter. So the tube diameter only has length in its dimension. So diameter gets a score of 1 for length, 0 for mass, and 0 for time. In the same way, velocity. Velocity has two dimensions. It's length and time. But we need to be careful what power those dimensions have been raised to. So length is raised to the power of 1. So velocity gets a 1 for length. Mass, it doesn't have mass. That means the mass has been raised to a power of 0. So that's going to be a 0. And then finally, time is raised to the power of -1. That's going to be -1 in the score. So in the same way, we're going to construct this entire table. So let's go ahead and do that. So density is 1, that's actually a 0, 1, and a -3. This is going to be -1, 1, -1. Then we have 2 here, 0, -1, 1, 0, -1. Okay, now that we've constructed this whole table, what we're going to do is make a matrix out of this, and that's going to be called our dimensional matrix. So how we do that is basically just keep all the things on the rows in the rows and everything in the columns in the columns. So let's go ahead and construct that matrix. So dimensional matrix dm is going to be equal to, so we have 1, 0, 0. So we're going to write that down as is, 1, 0, 0, and then 1, 0, -1, 1, 0, -1, and in the same way, we're just going to do the entire table. So that's 0, 1, -3, -1, 1, -1. That's 2, 0, -1, 1, 0, -1. Okay. Now that we have the dimensional matrix, what we want to do is calculate the rank of the dimensional matrix. So what is a rank? Rank is basically the total number of independent rows or the total number of independent columns that we have in this matrix. There is a hands-on method of doing this, but for the purposes of this video, we're going to do it in coding. So let's go over and head to Python and try to calculate what the rank of this matrix is. So we just calculated that the rank of the dimensional matrix we had was 3. So what was the point of doing that? Well, basically, the rank of this matrix allows us to find out just how many dimensional groups we're going to have in this situation. So the number of dimensional groups that we actually have is the total number of variables subtracted by the rank of the matrix. So we have 1, 2, 3, 4, 5, 6 variables. We subtract that by 3 and we end up with 3. So we're going to have 3 different dimensional groups. So let's go. I'm going to go ahead and write that. Number of dimensionless groups equals n minus rank, which is 6 minus 3, that is 3. Okay, so we know that we have 3 dimensionless groups, so let's represent that by pi 1, pi 2, and pi 3. So these are our dimensionless parameters. Now, each of these dimensional parameters are going to have what it's called a core group. So what is a core group? So a core group is basically a group of variables that we select from the variables that we already have that we will assign to each of our dimensionless parameters. So the question comes, like, if it's a group of variables, how many variables should we choose? Well, the answer's right here. So whatever the rank of our dimensional group is the number of variables that would be present in our core group. So yeah, in this problem, we're going to have 3 variables present in our core group. So the next question is, well, we have 6 different variables here. Which of these 3 should we choose in our core group? So there's only one rule to do that, and that is all the core groups, the union of all the core groups should contain all of the dimensions that are present here. So that means we have length, time, and mass. So if we need to choose 3 different variables that in their union will have all of these 3 dimensions. So for example, if I select diameter and then fluid velocity and mass transfer coefficient, that cannot be a core group because you see, we have length, time, length, time, but in all three, we don't have a single dimension of mass. So that cannot be used as a core group. Now, let's see, if we use the diameter, the density, and the mass diffusivity, if we'll have all of the dimensions or not. So diameter has got the length, and then from the density we can get the mass, and from diffusivity we can get time. So that group can be used as a core group. Another thing to note, although this is not a rule, is that it's always wise to not keep the variable that we're most interested in our core group. So a mass transfer is happening here. So right here, the variable that we're most interested in is the mass transfer coefficient. So we will not put that in the core group because we don't want this variable appearing in all of our dimensionless groups. We want to isolate it within one of these. So let's go ahead and write down our core group. So that's going to be the mass diffusivity, and then we have our density, and finally the diameter. So let's write that down in all of the dimensionless parameters. Now, we can't just stop at this. We're going to have to raise each of these variables by a different power. So we'll raise the diffusivity here by A, density by B, diameter by C, and the power has to be different in all of these. So this is going to be a D, E, F, not A, B, C, and then G, H, I. Now, the last thing left to do is we take all of the variables that are remaining and we distribute them among these dimensionless groups. So we have velocity remaining. So let's go with V, and then we have viscosity. So that's a mu. And then finally, we have the mass transfer coefficient. There we go. Now, the one thing to remember about these dimensionless groups is that they're dimensionless, which means they don't have units. So using that information, we can actually find out what the value of A, B, C, D, E, F, G, H, I are. So let's go ahead and do that. So our pi1 is equal to diffusivity is, the units of diffusivity is meters squared per second. So that's meters squared divided by second raised to the power of A. And then density. Density is kilograms per meters cubed. So that's kilograms divided by meters cubed raised to the power of B. Diameter is simply meter raised to the power of C, and velocity is meters per unit second. Okay, so you have that. And so let's go ahead and combine all the variables right away. So that's meters is going to be raised to the power of 2a minus 3b plus c plus 1. So that's meter. And then let's take a look at kilogram. For kilogram, we only have 1, so that's going to be kilogram raised to the power of b. And then finally, seconds, that's going to be raised to the power of a and 1. So that's raised to the power of negative a minus 1, because these both are in the denominator, so we'll have to use negative power. Now, since these are dimensionless groups, this should equal 0, this should equal 0, and this should equal 0. So right off the bat, we know that b is going to be equal to 0, and then negative a minus 1 is equal to 0, so that means a is equal to negative 1. And then finally, 2a minus 3b plus c plus 1 should also equal 0. We know that a is equal to negative 1, so that's going to be negative 2. We know b is equal to 0, so that's 0, plus c plus 1 is equal to 0, and therefore we know that c is equal to 1. So we found out what our B, A, and C are. So in the same way, we're going to solve all of this for pi 2 and pi 3 as well. So let's do that. So in this case, these two are like exactly the same. So from there, we can say that B, which is corresponding to H, is equal to 0. And then A, which corresponds to G, should equal -1. And then I, which corresponds to C, should equal 1. So finally, let's erase this part. We have all the values of A, B, C, all the way to I. Now let's write down our actual dimensionless groups. I'll write it down here. So our pi 1 is equal to the diffusivity coefficient raised to the power of -1 and density raised to 0, diameter raised to the power of 1, and velocity. Now, this can be written as Vd divided by dAb. And then our pi 2 is equal to diameter of, my bad, it's actually diffusivity coefficient, density, diameter, mu, and here we're going to raise this to the power of -1, this to the power of e, which is also -1, and finally f, which is equal to 0, and here we get viscosity divided by diffusion coefficient times the density. And finally, our third dimensionless group, that is, so this is going to be raised to the power of -1, density to the power of 0, and diameter to 1. So that is Kc divided by dAb times density. Looks like I made a little mistake here, so diameter should actually be in the numerator for our third dimensionless group because diameter has a power of 1. So yeah, okay. So all of these dimensionless numbers actually have a name to them. So our last one is actually the Sherwood number. Sherwood number, and that's denoted by SH. And this one is actually the Schmidt's number, denoted by SC, and this one is our Pickley number, defined by PE.
Well, now you might be wondering, are these combinations of variables that important that they should get the names of their own? Well, the short answer is yes, because the situation that we just looked at is a very general situation where convective mass transfer is happening. And every time there's a convective mass transfer, where the whole process is always going to be affected by what the diffusion coefficient is, what the mass transfer coefficient is, what the density and viscosity of the fluid is, and even an effective length, which in this case was the diameter of the pipe. So these variables are always going to be present in similar situations. And on top of that, what's going to happen is that more likely than not, you will probably find these variables in these exact combinations, which make up the Sherwood number, the Reynolds number, and the Schmidt's number. So yeah, these variables are very important.
So now let's try and divide the first two dimensionless groups, the Peclet number and the Schmidt's number, and see what result we get. So pi 1 divided by pi 2. Pi 1 is velocity times diameter divided by the mass diffusivity constant, and the pi 2 is viscosity divided by density times the mass diffusivity. Okay, so right off the bat, we see that these two things cancel out, and if we rearrange the variables, that's going to be velocity times diameter times density, all of which is divided by viscosity. Now we know this is actually equal to the Reynolds number. So there we have it.
So now we have a situation where a pure volatile liquid is dripping down the inner walls of a tube, and through this very same tube, a gas is being blown upwards. So now the gas and the liquid are in contact, so the liquid is going to diffuse into the gas, and there's a convective mass transfer going on. So in 1983, Gilliland and Sherwood studied this exact situation with 9 different liquids, and the conclusion they came up with was that the Sherwood number is equal to 0.023 times the Reynolds number raised to the power of 0.83 times the Schmidt's number raised to the power of 0.44. Today what we're going to do is we're going to be using experimental data for the Sherwood's number, Reynolds number, and Schmidt's number, and we're going to try to come up with the same conclusion that Gilliland and Sherwood did. And for this, we're going to be using mathematical methods, namely the Penrose inverse and the sum square difference method. And on top of this, we're also going to be graphically representing our collected data and our model, just to visually see how well our model predicts the observed data.
So to prove the relationship between our Sherwood number, Reynolds number, and Schmidt's number, we're going to first have to start off by assuming that our solution actually takes this form, where Sherwood's number is equal to a constant A multiplied by the Reynolds number raised to the power of B multiplied by the Schmidt's number raised to the power of C. Now, as to how I came up with this equation, there is some theoretical basis for it, but it's beyond the scope of this video, so I'm going to skip over that. You're just going to have to trust me. So once we look at this form, the most natural thing for us to do would be to try to calculate what each of these values are, each of these constants A, B, and C. Because when we do an experiment, we can collect all the variables we'll need in order to calculate our Sherwood's number, Reynolds number, and Schmidt's number, whereas A, B, and C could be any arbitrary number. So let's go ahead and try to calculate those values. First of all, we see that the constants B and C are in the exponents. So the easiest thing for us to do right now would be to take the natural log of on the both sides so that the constants get out of the exponent. So let's go ahead and do that. So that's going to be the natural log of the Schmidt's number equals the natural log of A plus B times the natural log of the Reynolds number plus C times the natural log of the Schmidt's number. Okay, so we're here. Now, when we do an experiment, we're probably going to do it a very large number of times so that we get a better, more accurate result for our equation. So let's assume that for this experiment, we did it 100 times. So we have 100 different values for our Schmidt's number, Reynolds number, and Sherwood number. So in a case like this, I would say doing it as in a matrix form would be the easiest because it takes into account all of the 100 experiments we're going to do. So I'm going to write this down in a matrix form. So let's see what that's going to be like. So I'll go ahead and write the natural log of Sherwood number 1, the natural log of Sherwood number 2, natural log of Sherwood number 3, and this keeps going on and on until 100 Sherwood numbers are done. So that's our one side, and this I'm going to write as
1, 1, 1, the natural log of Reynolds number 1, the natural log of Reynolds number 2, and the natural log of Reynolds number 3. Similarly, it's the natural log of Schmidt's number 1, the natural log of Schmidt's number 2, and the natural log of Schmidt's number 3.
And this keeps going on until 100 values have been down. And then finally, we have natural log of A, then B, and then C. Now, if you look at the right-hand side of the equations, it might look a little bit weird. It definitely looks different from what we have on the second step, but if you do a matrix multiplication of these two matrices, you will end up with that equation, because it's simply going to be 1 times natural log of A plus natural log of the Reynolds number times B plus natural log of Schmidt's number times C, which is what we have in the second step. So that's how we represent them in the matrix form. So as I already said, we've done this experiment 100 times. So the dimension of this matrix is going to be 100 by 1, because we're going to have 100 rows and a single column. The dimension of this matrix is going to be 100 rows and 3 columns. So that's 100 by 3. And the dimension of this matrix is going to be 3 by 1. And it's a very small matrix. Now, we have a very weird situation here where we have 100 different equations, but we only have 3 unknowns, because Sherwood number, Reynolds number, and Schmidt's number can be calculated from experimental values, whereas these constants cannot. So in normal situations, if we were calculating something theoretical, just solving 3 equations, like picking any 3 equations from the 100 equations, would give you a value for A, B, and C. However, we need to remember that we're finding out these values with experimental data, which is prone to error. So if we only take 3 values and try to calculate A, B, and C, say the equations might be true for Sherwood number 1, but it may not be true for Sherwood number, say, 99. So we have to take into account all of the 100 equations that we just wrote down. So what do we do about it? And the solution is in what we call the Penrose inverse. So in order to do that, I'm going to represent all of these matrices as variables. So let's go ahead and do that. So I'm going to represent our Sherwood numbers by the variable y. And that's our 100 by 1 matrix equal to, now this matrix, which I'm going to call our design matrix, will be represented by X. This is 100 by 3 matrix. And our variables, our unknowns, I will be representing it by the letter B. And that's 3 by 1. So we have this relationship going on. All right, so I've rearranged this equation. I just switched the left-hand side with the right-hand side. So let's see what we can do here. The problem that we're trying to solve is that how we can take all the 100 variables into account to calculate just 3 unknowns. So first of all, let's start by multiplying both of these sides by the transpose of matrix X. A transpose of a matrix is simply the elements on the rows are switched to the columns, and those in the columns are switched to the rows. So the inverse matrix of X sub t, will have the dimension of 3 by 100. So we multiply that on both sides. So we're left with this. It looks like I made a little error here in the dimensions. Okay, so if we multiply these two matrices, the transpose of x and x, what we'll get is a matrix that is 3 by 3. So I'll go ahead and rewrite it. So the transpose of x times x matrix is going to be of dimension 3 by 3. And then we have our variable matrix 3 by 1, which is equal to the transpose of x times the y matrix. Okay, so our end goal is to try to calculate what the value of our unknowns are, and the unknowns are in our matrix B, so it makes sense that we isolate B, like keep matrix B on one side of the equation and keep everything else on the other side. So in order to do that, what I'll do is multiply both sides by the inverse of the matrix, which is the product of matrix X and the transpose of matrix X. So let's do that. So I'm going to multiply both sides by transpose of x times x whole inversed. And this is also going to be a 3 by 3 matrix. So let's go ahead and put that there as well. That's transpose of x times x raised to the power of -1, 3 by 3. Now, we know that any matrix multiplied by its inverse is equal to the identity matrix. And the identity matrix multiplied by another matrix is always equal to the other matrix. Okay, so the result of this whole left-hand side is simply going to be the matrix B. And what we have left on the other side is the transpose of matrix X times X inverse times the transpose of X times the matrix Y. So this relationship is what we obtain from our Penrose inverse. So we can see that the transpose of matrix X is 100 by 3. The matrix X itself is also 100 by 3. And Y matrix is 100 by 1. So we can see that all the 100 values that we collected in our experiment have been taken into account to find the 3 unknowns that we have in matrix B. So that's how we're going to use Penrose inverse in order to find our constants A, B, and C. We are not going to do that on the board. We're going to code that out in Python. And so let's see what values we get for A, B, and C. All right, so now we're in Python, and now we're going to try to solve the Penrose inverse in order to find what the actual values of our constant A, B, and C are going to be. So first of all, in order to do this, I'm going to have to import the NumPy library. So let's go ahead and do that. I will import it as np. There you go. Now, in order to solve this actual problem, I'm going to have to feed some data into it. I have this data copied in my clipboard, and I'm just going to paste it and run it. I am not going to explain how this data was calculated because it's just going to cause some confusion right now. So once I've solved this entire problem, I'm going to go back to this line, cell 2, and explain how exactly I got that data from. But for now, just trust me, that's a good data. So the next step. As we can see from the Penrose inverse equation that I wrote down there, we need to input what our cells, our matrices X, Y, and B are going to be. So first of all, let's write down what our matrix X is going to be. So X has 3 different columns. The first column has nothing but 1. The second column has all the Reynolds numbers, whereas the third column has all the Schmidt numbers. So let's write that in a parentheses before I declare a variable for it. So the first one is just an array, should just be an array of the number 1. So what I'm going to do is np dot ones underscore like re. So what this line exactly does is that it makes an array of only the number 1, but this array is going to be identical, not identical. So what it's going to do is basically it's going to take my array of Reynolds numbers, and it's going to replace every single number in that array by the number 1. So let's see what I exactly mean by that. So first of all, let's see what my Reynolds number is going to be. So these are my 100 values for the Reynolds number, and if I do np dot ones underscore like Reynolds number, what I get is this array. So basically every single number in the Reynolds number array has been replaced by 1. So that is the first column that we need. Our second column is basically the natural log of all the Reynolds numbers. So that's going to be np.log of our Reynolds numbers. And finally, on the third column, we have the natural log of the Schmidt number. So that's going to be np.log, natural log of the Schmidt number. So yeah, these are the 3 things that we need for our matrix X. Since these 3 items are stacked in a column, what I'm going to do is, let's enclose this in large brackets because we want an array, and then within parentheses. So what I'm going to do is np dot column stack. So basically what this is going to do is it's going to put all of these 3 things in 1 column each. So let's run this code and see what it looks like. So there it is. So all the 1 is in 1 column, all my Reynolds numbers are in another column, and all my Schmidt numbers are in the final column. So that I will be storing in the variable x. There we have it. And so what do we do for y? So we can see that our matrix y is basically the natural log of all of our Sherwood numbers. So that's y is basically going to be the np dot natural log of the Sherwood numbers. So we have our x and y. Now, our matrix B that we need to calculate is written out right there. So first of all, we need to find out what the transpose of matrix X is going to be. It's fairly easy to transpose a matrix in Python. What you basically do is take the matrix and write down dot uppercase T, and it just transposes our matrix for us. So that's our X transpose T. Now we need to also find what the product of the transpose of X and X is going to be. So this is going to be a matrix multiplication, so we can't simply just type x dot t times x. This is not going to work because it's a matrix and we're doing an algebraic multiplication here. So in order to do a matrix multiplication, we simply replace the multiply sign by and at the rate. So that's going to give us our 3 by 3 matrix that we talked about earlier. So we have that. The next step is to find the actual inverse of this whole multiplication. Now, the way to do this in Python is basically typing np.linalg for linear algebra .inv for inverse. So the inverse of our multiplication is basically this result that we just got. So if we matrix multiply this inverse by the transpose of tx and multiply that by the y matrix, we're basically going to get our matrix B, which is what we've been looking for all along, because matrix B has our A, B, and C. So right off the bat, we can see that the value of the constant B is 8.3609 and C is 0.3943. And what we're gonna do, the value of A is not negative 3.79 because the first element of our array, of our matrix B, is actually the natural log of A, not A. So in order to calculate it, we're basically going to have to find the exponent of this number right here. So in order to do that, I'm going to store this whole array in the variable B. And now my variable A is going to, now constant A is going to equal np.exp. Basically, I'm raising this by the power of E. No, I'm raising E raised to the power of the first element of the array B. And since we're already here, let's store the second value in the variable lowercase b and the third value in the variable up lowercase c. So that's B1. So there we have it. So our variable A is equal to, our constant A is equal to 0.022, which is almost equal to the answer that we want, which is 0.023. And then our variable B is equal to, it looks like I made a little mistake here. So it should be 1 here and 2 there. My bad. Okay, so let's see what our variable B looks like. Our constant B is equal to 0.836, which is very close to 0.83, the actual value that we need. And then our variable C is equal to 0.39. This is also very close to the value of 0.44 that we need. So yeah, so by this method, we can calculate A, B, and C. Now, as I promised, I need to explain the second cell of this whole script. So what I basically did here is that for the Reynolds number, I created an array of random values. So let's look at how I did that. I did np.random.uniform. This basically makes an array of random values, random uniform values. And the range for the array I gave it was 2000 being the minimum number and the maximum number being 35,000. And I wanted 100 values inside my array. So that's how I created my Reynolds number. So this, something like this would be my Reynolds number. Since this is randomly generated, the Reynolds number that I got here may not be the same as I got here, because every time I run this line of code, the Reynolds number is going to change. For example, we have 20,156 right now. If I run this code again, yeah, that's changes to 19,516. So yeah, that's how I got the Reynolds number. For the Schmitz number, it's basically the same idea, except the range has been changed. It's been changed from 0.6 to 2.5 instead of 2,000 to 35,000. Now, after this, what I did is that I actually used the equation that we have itself in order to calculate the Schmitz number based on the two random values of Reynolds number and Schmitz number that we got. So I pretty much just calculated what the Sherwood number would be based on the random values of Reynolds number and Schmitz number. And then what I did was okay, let me do this part once more time. So what I did was np.random.normal. So this means I'm trying to create a normal distribution. And my normal distribution has mean, LOC, location, which means mean, the center of the normal distribution, at the Sherwood number, the calculated Sherwood number, the number that we just calculated right here. So that, and scale at 10% of the Sherwood number that we calculated. So what this means is that I took the original Sherwood number and I made a normal distribution out of it, and I introduced an error of 10% within those values. So what this line of code does is basically it generates a random set of values based on my originally calculated Sherwood number, and and it makes it randomly distributed such that there's a 10% error in all of these values. So yeah, it sounds like something that's extremely stupid to do because we're using the actual equation to make a experimental data, and we're using that to prove that the original equation is true. So yeah, it sounds stupid, but in reality, this is pretty much how it works. Because like if we were to go out in the real world and do this experiment, you would get a normal distribution of values that are based on our equation right there with some percentage error. So that's basically how I did that. So yeah, this is one way to uh, explain this equation right here. And yeah. So the second way that we can find out what the values for our unknown constants A, B, and C are is what's called a sum squared difference method. So what do I mean by that? So we have our actual equation, which we assume to be true. And what we want to do is see if our observed value, how different our observed value is from a calculated value. So what we're going to do for that is make a guess for A, B, and C, and then we're going to try to calculate the right-hand side of the equation, since we already know what the Reynolds number and Schmidt's number are going to be from our experimentation. And we're going to subtract that from the Sherwood number that we also got from the experiment, and we're going to see what the difference between those are. And we're going to make multiple guesses for it, and then we're going to see which combination of A, B, and C gives us the minimum possible value of the difference between the left-hand side and right-hand side of the equation. So let's go a little bit more in depth about this method. So right here, I have a simple two-dimensional graph with two variables, x and y. The line that's going right through the points are our observed values. So we directly did an experiment and found both x and y to go on a line like this. And the axes that you see on the graph are what we got by making a guess for A and B. For example, I assumed A to be, say, 0.1 and B to be 0.03. And using that, I took a value of x from our experiment and then calculated this value, only the right-hand side of the equation. And then I plotted whatever the answer from that calculation was. I did not use the observed value of y. So keep that in mind. So I got all